In this video, we talk about the Infinitesimal Generator. That's a really cool name. I think this sounds really good. So here the question is, assume you know the semigroup already. How can you find the corresponding A? So in other words, let's say you know e to the at already. How can we get the A? Well, what we can do is we can differentiate by t, and then we sub in t is 0. Okay, so then you get a e to the at. T is 0, so you get a e to the 0, so this is a. And this is what we like to do in general. So here on the left, I wrote down the differential quotient for this derivative as h goes to 0, e to the ah minus e to the 0 divided by h. And this goes to a if all of this exists. So this will be our definition for the infinitesimal generator. So let T be a strongly continuous semigroup, and then the infinitesimal generator is the limit as h goes to 0, t of hx minus x divided by h. And then we make it very simple. So maybe this exists or not, so we just put this in the domain. So whenever this limit exists, we call it in the domain, and if it does not exist, then it's not in the domain. Before we do anything else, let's look at our wonderful example of the left shift semigroup. T of t u of x is u of x plus t, and compute this differential quotient. So then au would be the limit as just defined. But now, looking at this term here, we just shift the first expression, so we have u of x plus h minus u of x divided by h, and this is the wonderful partial derivative. Or actually, u here depends only on one variable, so it's the normal derivative with respect to x. Beautiful. So then we have a is equal to d by dx with domain C1, right? The domain are all functions which are differentiable. Ha, that was easy. That was nice. And actually, this carries much further because we have basically a fundamental theorem of calculus, but this time we have it for semigroups. So I call this the fundamental theorem for semigroups. And it tells you that if you have a semigroup, you can play around with a generator as if you would have the corresponding differential equation. Now these items 1, 2, 3, 4, they go all in the similar direction, but it's worthwhile to write them all out. So let's start with the first one. So here we integrate from t to t plus h and then divide by 1 over h. So what we basically do is we differentiate the integral. And as we know from calculus, differentiation undoes integration, and the same is true here. So this differential quotient of the integral goes to tt of x. Moreover, if we have x in the Banach space, then t, the integral with t of s, lifts it into the domain. Okay, so integral 0 to t, t of s x ds will be in the domain, which means we can apply a, and the limit exists. So let's apply a to this integral here, and then the result says we get ttx minus x. Of course, this is something we need to prove. Now, if we start already in the domain of definition, then the semigroup will keep us there. So meaning the domain of definition for A is invariant under T. And then the map T maps to TTX is differentiable, and we have a differential equation d by dt of semigroup X is equal to A applied to the semigroup, or a semigroup applied to AX. So, in other words, here we have u dot equals AU. Okay, so if we start with a semigroup, we can derive a differential equation u dot AU so that T is the solution. And then finally, number 4, again on the domain of definition of A, we can integrate the differential equation and then we get an integrated version of the same thing. Let's go over the proof. So first of all, t is strongly continuous, which means it is continuous at 0, at time t is 0. So if I send t of s where s goes to 0, then the integrand goes to 0, and so the whole thing then has a length h, and then divided by 1 over h, and this also goes to 0. So limit h to 0, 1 over h, integral 0 to h, and then this expression, this goes to 0. You can also take the operator norm of this expression and then see the same thing. So now we can use the semigroup property and do this for an integral from t to t plus h. So we advance everything by t, because now we can take out the little t thing, and then we get an integral from 0 to h. Okay, so that's how we used the semigroup property here. And then we use the previous result from the previous page, so that this guy here goes actually to t0, and t0 is the identity, so then we have t of tx. For the second result, we want to apply a to the integral. So we apply a in the discrete form, or a in the limit form, right? So we use t of h minus identity divided by h, and then later we want to go to the limit as h goes to 0. So we apply this to the integral from 0 to t of sx. So then what we do is we multiply this, and we multiply that, and then we get two terms. So then the first term will be advancing s by h, this is here, and the second term will be the identity, so it's just t of s. And now I split up the integrations in a funny way. So from the first bit, I take the integral from 0 to t minus h here, and then from t minus h to t, I take that here. So this comes from the first term, and then from the second term, the minus ts, I take an integral from h to t here, and then from 0 to h here, and obeying the minus sign. So this comes from the second term. Now the first two terms cancel. So here, these two terms, right, in the first we have an integral from 0 to t minus h, where capital T is shifted by h, s plus h. Minus, and here we have an integral from h to t, where t is not shifted. So in the end, it's the same, right? We can shift the first integral by minus h, and then we also get an integral from h to t. So these guys cancel, and the other two remain. Now for this fellow here, I do a shift of the h. Okay, so then this becomes that here, from t to t plus h, and the other one I leave unchanged. So now I have it in a form which I just did under item number 1. The first one goes to t of tx, and the last one just goes to the identity times x, as h goes to 0. So meaning this limit exists, so I can actually apply. So this goes then to a times the integral from 0 to t of s x ds. Oh, this is almost unreadable. But you know what I mean. The first bit converges to a. We can apply everything. Limits exist, and so on. All right. Number 3. Let us look at the time derivatives. I just write down t of t plus h x minus t of t x divided by h. This goes to the partial derivative by t. And using the semigroup, I can take the t out to the front, to the back, or I can take it out to the front. And then what I keep is just the th minus identity divided by h, either in the front or in the back, which then goes to a. So then I have the formulas for the differential equations. d by dt of the semigroup is a times the semigroup, which is also semigroup times a. Now for the last relationship, we just integrate item 3 using the fundamental theorem of calculus. So it does come back. Let's look at item 4 just quickly here. Okay, so t of t minus t of s. So this is the integral of the time derivative. And then we integrate the right-hand side. Yoo-hoo! So that's all easy. Okay, so having a semigroup, we can define an infinitesimal generator which has all these beautiful properties, which remind very much of ODE theory. Then there's one more result which I like to cover right now, and this is theorem 8.2.2. So if we have an infinitesimal generator, then the domain is dense and the operator is closed. And this is actually a very important result in applications, because often we have the opposite situation. We have a generator and we want to know if we can find a semigroup. And so the necessary conditions would be that the domain is dense and that A is closed. So if you read papers about this kind of stuff, this is what people do first. They first ensure that the domain is dense and that the operator is closed. Otherwise, they have to do something else. Okay, but now we go from the other direction. So we have a semigroup, we have a generator. Now we want to show domain is dense and the operator is closed. The denseness is actually rather simple. So from the previous fundamental theorem, we know that x can be written as a limit h goes to 0. So I'm here now, integral 0 to h t of s x ds. But we know that this bit is in the domain. So I wrote here again. This is in the domain. So meaning x is approximated by elements in the domain. And that is the very definition of being dense. So this is dense. Now for closeness, we consider a convergent sequence. xn in the domain, xn goes to x, axn goes to y. And we need to show that the limit is obeyed so that y is equal to ax. Yeah, and we use the previous theorem there. So one result says that thxn minus xn equals the integral from 0 to h tsaxn. And now we take the limit term by term. So the first term converges to thx minus x, and the right-hand side converges to integral tsy ds, because axn converges to y. And then we can apply the limit as h goes to 0, and then the left-hand side goes to a, and the right, which is written here again, and the right-hand side goes to this limit, which actually turns out to be y. So this is a very straightforward proof, just using properties from the fundamental theorem. So remember, we start with a semigroup, we find the infinitesimal generator as a derivative, and then this A has a dense domain and is a closed operator. It doesn't have to be bounded, and it will not be bounded in many examples, but it has to be closed.